Well, I'm Josh. I'm Team 21, and we're K3TU, and we've done the amateur radio weather transponder. This is our abstract. If you would like to read it further, please check our website for the design document, and it should also be posted outside. Our motivation for this is because the amateur radio club at Temple is not able to detect weather situations with its station, and we just figure it is something that everybody is able to make use of, and the nearest station is approximately 8 miles from the campus, so we decided to make a weather station. Our technical constraints are it needs to be weatherproof, it needs to withstand high wind speeds and excessive downpours, it needs to be placed in a lightning protected area, and it needs to be able to still function in the ranges relative to extreme winters and summers in Philadelphia, and it needs to be able to check for corrupted data. Non-technical design constraints, it needs to be under our $500 budget. We want to limit the maintenance, so no refillable parts, and something that's very true in many of Dr. Szilagyi's projects, we want to be able to reuse the parts in it for other projects. And we want it to be easily accessible, because even though it's going to be up on the roof, you want to check to make sure if there are any problems. And health and safety, again, it's on the roof, so when the wind starts blowing, you don't want it to fall off. This is our overview of the project. Again, weather happens, the sensors will detect it. The sensors will send their information to the microcomputer when the microcomputer tells it to send the information. And then when it's integrated with the radio station, we want to have a modem send the information to it, and it will need a multiplexer to integrate it with the existing system and to finally transmit it over the radio station. Our team is our Swiss Army knife leader, Steve Long. He helps with coordinating hardware and software, mainly the hardware. Cassandra Lee and Robert Brown are the software team. I'm Josh Hellriegel, and I design the hardware. And Dennis Szilagyi is our advisor, who has a doctorate degree. And we're going to start with software, which is still pretty cool. The tasks of the software team are to edit the OneWire library. We were able to find a OneWire library code online, but it still needs editing. Then once we receive the data from the sensors, it still needs to be decoded. And finally, we want to throw it up on a really nice looking graphical user interface, or a GUI. So when you want to get information from a sensor, after you try and find it, it sends back a CRC. If this CRC is valid, then you print the corresponding address that it has with it into the ROM. Therefore, you're able to send a specific signal set in order to mess around with the sensor, and then you'll receive the raw data from it. And then you need to look at the data sheet and figure out how to edit this raw data to get your degrees Celsius, your miles per hour, and you need to repeat this process for every single sensor. For example, here R is your address and P is the raw data. In this example, 10 is the temperature sensor, and then using the data sheet information here, you would decode the raw information. And using the serial information obtained from our microcomputer through USB, you would use that information to throw it up on our graphical user interface that was made in Visual Basic, which again displays a very nice Now for the hardware part of it, my task is to link all the one-wire sensors, which at first is a very easy task. And then I need to interface these one-wire sensors with our microcomputer, the MAX32, and our non-one-wire weather sensors, our rain sensor, and it needs a counter chip in order to keep track of rain levels. And then this non-one-wire sensor needs to be integrated into the one-wire network, and I need to then design voltage levels so that everything gets power. So our one-wire sensors are for temperature, wind speed, wind direction, humidity, and air pressure. As you can see, the wind instrument over there, the TAI 8515, can do all three of these. And our humidity and air pressure sensor look like the one over there. Basically, one wire means that in the same wire you get the voltage to power the device and the data that you want to collect. And so if your microcontroller sends out an appropriate voltage, then all that you need to do is just attach them one right after another and another through these ports, which are RJ11s, which are basically telephone cables. The microcontroller that we want to use is the MAX32. It has a lot of power, but the issue with it is it sends out a 3.3 volt signal, and we need 5 volts in order for the weather sensors to operate correctly. So therefore, we need to make level shifters, and we tested the design out in multi-sim, and it successfully changes, it scales up the voltage from 3.3 to 5, and then when the signals are coming back from the weather sensors, it goes back to 3.3 volts. And because these level shifters are not bi-directional like one-wire, like our one-wire buses, we need to make sure that when the information is coming back from the sensors that it doesn't go the wrong way. Therefore, we have a tri-state logic buffer in the setup. And the reason why we have one that has 4 channels is because one of the setups we were considering would use 2 of these, but currently we only use 1 channel. And this just shows that when you put in 0 volts into the enable, it still lets the 5 volts through. However, the output is still only 3.6 volts, which is important for later. And again, you put voltage into the enable and your 5 volts doesn't make it through, and you just get millivolts. This is our level shifter setup, and again, the information comes out of the MAX32, gets shifted up. We want the enable to be low so that it can get through. It then goes to the sensors, and then when it comes back, we want enable to be high so that the signal doesn't go the wrong direction. And then it comes back and it gets scaled back down to 3.3 volts. And this is the construction of the MAX32 with the level shifter circuit. And this is the rain sensor. It's really fancy compared to the one-wire sensors. And again, it's not one wire. It requires 12 volts to be powered, and the counter chip that it needs in order to keep track of rain levels, it needs another 5 volts. So this is the connection between all the sensors. In terms of data distribution, from the pressure, humidity, and wind, it's straightforward, but it needs to split and go into the counter chip, which then goes into the rain sensor, and that's how data distribution is handled. Now, need to deal with how to get voltage to all the sensors. We used voltage regulators in this setup. The data sheet for it gives you this equation to help figure out what your voltage out is going to be. But of course, the real world happens and you can only get a good rough estimate on where to start. So we changed the resistor values until we got something relatively close, and we wanted it above 5 volts. So we tested it and it successfully changed 12 volts to 5. And there are actually 2 voltage regulators on that setup, but we are no longer using the 10 volt setup, but it can be there if somebody has a device that requires 10 volts. Now, just to get straight, what is on the outside and what's indoors with the computer is this kind of silly drawing. Up on the roof is going to be the weather station, and inside the weather box are going to be our 2 sensors, or 4 sensors, 2 of them inside the weather box, along with our voltage regulators. And then back on the ground is going to be a black box with the Max 32 and the 12 volt inputs. And we're going to connect the 2 with a 100-foot Ethernet cable that's going to travel up and have data, ground, 12 volts, and its ground in it. And now we're going to show an example of our weather station. And so right now there's a glitch where it shows 180 some degrees, but it should go back down to the actual temperature of 69.3 now. It's obviously not windy in here. Our air pressure sensor right now is not working, and the humidity is a nice, 49.3, and it's not raining in here. You can put it back to the PowerPoint. The rain sensor, by clicking here, we have the sensitivity set up a lot, and each click probably now means, 1% of an inch of rain, and so it'll flash green. We tested all of our sensors to make sure that they're accurate. This is our bill of materials. While you're looking at it, we inherited several different sensors from a previous team, which definitely helped us keep our costs low. So humidity, pressure, and wind didn't cost us anything. Our current status, this is our Gantt chart for our current schedule, but just to explain what our current situation is. Our pressure sensor, we were able to get a reading out of it, but doing several different tests where we are sure that we changed the pressure in its relative area, it's still spitting out the same exact number, which is strange because a lot of the other sensors, when they're just broken, they don't give you back an address to get information from. Our rain sensor right now is arguing with the wind sensor because the wind sensor has its own counter chip, and they're screaming at each other. And in order to have the Max 32 work with the one-wire library, a couple hundred lines of code need to be edited. So for now, we are going to use the Arduino Uno. references again if you want to look at the design document. And we'd like to thank the physics department for helping us out with getting testing equipment. The engineering building roof, because it's going to have lightning protection on it, so we don't need to buy it for our weather station. And Dr. Salaji, of course, because he gave us lab space and many circuit components, so we didn't need to wait a week for resistors to ship. And I'll take questions now.
No questions? Come on.
I'm kind of curious how the rain sensor works.
Yes, the rain sensor, what it does is when it does that flash, it sends the 5-volt signal through to the counter chip, so it keeps track of like how many tenths of inches of rain has fallen. So like when I made it flash, it's basically feeling the rainfall, and again, the counter chip will keep track of this. There's also a software method of doing it, but when we wanted to integrate a non-one-wire sensor into this, it also has to do with editing the code, but we wanted to have to edit the hardware as well.
So does it measure the rain by weight?
I don't think it does, because it emits infrared, so I guess it's more of a visual, I can't think of it.
I mean, it measures the transmission of the infrared through the water that accumulates?
I would have to look on the data sheet. No.
Does the water accumulate inside of that?
No, it does not. The top, or the weather.
No,
box,
yeah.
Yeah, at first it did when we got it, but the top corners are caulked, but the bottom ones aren't, in case it does seep in.
Well, when the rain falls on the sensor is at the very top, right? Does the water accumulate in the sensor?
No, it slides off and it's waterproof.
So it self-empties?
Like,
What?
it's not a tipping bucket or anything
Yeah.
like that, so it doesn't collect the water.
Okay.
Again, it's a lot more high-tech than the other one-wire sensors.
Are there any other questions? No? Thank our speaker.